filters are second order. So the nth order of the filter is directly affected by n poles in the filter design. The number of poles is indicated by the number of RC elements present in the circuit. Fundamentally, an increase in the number of poles will increase the roll off rate by 20 decibel per decade per pole. Okay, so if you have, like I mentioned before, 2 poles means negative 40 decibels, 3 poles 60 decibels, 4 poles is 80 decibels. Okay, thus a second order filter will have a negative decibel per decade roll off rate, which is much steeper than the roll off rate of the first order. And I think I have mentioned in the previous video that the most designs of these second order filters are generally named after the inventor, where we have a common filter such as Butterworth, Chebyshev, Bessel's, Salenky, for example. And all this type of filter is actually available in the low pass filter, high pass filter, and band pass filter, as well as a band stop notch filter configurations. Actually, this Salenky is one of the most widely known and popular second order filter design, because it's only require one single op amp to have gain control of the second order filter. Second order filter which has a steepest transition between the pass band to the stop band. Okay, so this is a generalized unity gain Salenky topology. So we have, you just remember this kind of configuration. So we have Vin that is connected to Z1, and then it has a feedback to the op amp, and then afterwards we have Z2 and Z4 that is connected to ground. And this is as usual the configuration for unity gain. Okay, so the difference between the high pass filter and low pass filter configuration for this Salenky is just the location of the capacitor and resistor. So for this generalized topology of a Salenky filter, you can have the transfer function of V out over V in of the system is given by this Z3 Z4 over Z1 Z2 plus Z1 Z3 plus Z2 Z3 plus Z3 and Z4. It is sometimes we can use different value of resistor and capacitor in this Salenky topology. When we do that, we can calculate for the cutoff frequency that is given by 1 over 2 pi R1 square root of R1, R2, C1 and C2. Okay, where does 2 pi comes? It's actually it comes from this omega, and 2 pi f. Omega equals to 2 pi f. So if either you can use omega c or fc, it depends, but you have to compensate for f for 2 pi if you use the frequency fc. So if resistor and capacitor values are the same, means R1 equals to R2 and C1 equals to C2, we can simplify the cutoff frequency of the filter by just taking this Fc equals to 1 over 2 pi Rc, or you can have omega c equals to 1 over Rc. Alright, so this is a low pass filter unity gain for the Salenky. As usual, when we said about low pass filter, so what comes first after the voltage in is actually resistor. Okay, so we have resistor, and then in feedback we have capacitor, and the capacitor that is connected to the ground. So this is, you can just memorize one either low pass filter or high pass filter, and remember one just low pass filter, and you can get the high pass filter configuration as well. It's just a compensation from low pass filter for the high pass filter. Okay, so you just replace the value of R1 Z into the R and C into the term TS. So what you get is this is for the transfer function for low pass filter silent key with unity gain. Okay, if you have some time that you can spend, you can just prove the expression of AV for the low pass filter to have this. Okay, so this is you can get the magnitude of this TS term, and you can get the gain for the unity silent key filter as something like this. Okay, the omega C will be attenuated at -6 decibels per decade. So you have this kind of, so this is the frequency, and then this is the gain here, and this is actually -6 decibels per decade. And the cutoff frequency is located at -6 decibels because it's actually and the slope is -dB per decade, because this is a second order system which has two capacitors. So two capacitors means we have two poles. When we have two poles means we have -20 decibel multiplied by 2, we have -40 decibels. Okay? And the roll-off rate is -40 decibel per decade. So this is a normalized low pass frequency response. Okay. Okay, this is a first order, and then this is a second order. And you also remember that we have mentioned earlier, when we said about second order system, it will also have the component of damping factor as well as the quality factor. Zeta damping factor is Q is quality factor. So both will affect the response of this filter. So if we have low value of zeta, which means you have high value of quality factor, what you get is you get a response that have you have a peak. You have a peak on the cutoff frequency region. So the higher the value of Q or the lower the value of zeta, the higher the peak will be. In this case, you can see that zeta equals to 0.7071. You can get a very smooth plot here. That is same as our cutoff frequency at -3 decibel per decade. Okay, then if you have a value zeta that is higher than 1, so the system will have a response that we call as overdamp. Okay, it will not have oscillation, it will not have any peak on this cutoff frequency region. And the response or the design of this value of Q or zeta is depends on the what are the things that can or you want to design. Next, okay, so I have explained in the previous video about this quality factor and damping ratio. You just take a look at that at the video, and I also included some examples that you can see. You just follow these websites and many other websites that actually you can see the examples for a second order filter. And now we have high pass filter, again using the silent key topology. Now what we have is actually we have the capacitor that is connected to the V input, and then we have resistor that is connected to the ground. So again, this is a unity gain filter, second order filter. Assuming R1 equals to R2 and C1 equals to C2, we can get this transfer function of this high pass filter. And then you can get this expression by taking the magnitude of this you can get the term here. That's it. For high pass filter, again, when you have a second order high pass filter, you will have 40 decibel per decade. This is not actually negative, it should be positive, and the slope should be positive because it's inclining, not declining position.